Okay, hello everyone. So as I may have mentioned before, my goal here is to have you guys learn everything you need to know about hypothesis testing. That's sort of the end of the semester. We don't get to hypothesis testing until Unit 3, in which case we look at hypothesis testing and then we look at a bunch of different hypothesis tests. Anyway, so I want to give a little rundown of what hypothesis testing is. And so here's the idea. First, what you do is you make an assumption. And I want to see this written on the slide. So go ahead, write this down. Make assumption. Then we want to know if that's a good assumption or not. Well, what we do is we make the assumption and we have a sample. We have some data. And then we use that assumption to compute a probability about sample. And so we get this likelihood of the data that we got. We compute a probability. And then what we do is we look at that probability. Is the sample unlikely? Is it significantly low or high? Is it unlikely? Is it significantly low or is it significantly high? If yes, so let's see. So is the sample unlikely? If yes, then reject the null. Reject the assumption. Because our sample has no reason to actually be unlikely. It's just a normal sample taken right out of reality. And so we reject our assumption. That's caused to think that the assumption is wrong. However, if no, that is to say, if the sample is not unlikely, then fail to reject assumption. The very center of all this is this likelihood. Whoops. And that is why we're talking about probability. That's why we talked about the Poisson and the binomial random variables. So we can get at that likelihood and get actual numerical evidence that the assumption is not correct, or fail to do so. And so that's hypothesis testing, and this is what we're talking about here. Okay, well, with that, let's go ahead and jump into Chapter 5 and 6, and we pretty much cover 6.2 in this slide deck. All right, so I'd like to see all this written out. So you'll probably be writing this out a few times. I wonder, the hope is that when we get to hypothesis testing, you'll already have an idea of this framework, and you'll really be able to get it down. There's going to be a series of quizzes that I'm designing about hypothesis testing that, that you'll be able to take as many times as it takes to do well. Those will go a lot easier if you take the time to try and understand what it is I'm saying here. All right. Okay, so the agenda for today. First, we're going to talk about continuous random variables. Okay, so these are random variables that have a continuous range or possible outputs. The first such variable is called a uniform distribution, or a uniform random variable. We're going to discuss that, and we're going to look at an example. Then after that, we're going to talk about the standard normal distribution, which is an incredible distribution. We see it all the time in nature. And so we're going to talk about what that is. And then we're going to have example after example after example. And then we'll talk about critical values, which we've sort of already seen. This is the z-score. This is related to z-score. And then we're going to talk about the not standard normal distribution, the normal distribution. So we'll just call that the normal distribution. That's just as opposed to standard normal distribution. Okay, great. So continuous probability distributions. Properties of continuous probability distributions. The area under the graph. Okay, so there's going to be this. So now the probability distribution is, so before it was a histogram, right? This sort of, the graph of it was this histogram, and it was like outcome 1, and then outcome 2 had a particular probability. So it was like 0, 1, 2, and they had these probabilities, right? But because this is continuous, each individual outcome has a very, very, very small probability. And so this sort of frequency plot with probability on the y-axis, is not appropriate anymore. And so what we end up having is what's called this density curve. Anyway, but we'll talk about that. The area under the graph of a continuous probability distribution is going to be equal to 1. And we will see that there is a correspondence between what? Between area and probability. Okay, so probabilities can be found by identifying the corresponding area of the graph. And that is the graph of what? The graph of the density curve. This is the graph that tells us about the probability distribution. Okay, the graph of any continuous probability distribution is called a density curve. And any density curve must satisfy the requirement that the total area under that curve is exactly 1. Because the total area under any density curve is equal to 1, there is a correspondence between, again, area and probability. And this is super important to understand. All right. Now, the uniform distribution is an example here. This is a continuous random variable, or a continuous random variable has a uniform distribution if its values are spread evenly. So each value within a particular range is equally as likely as the other values, as any other value. Over the range of possibilities. Okay. The graph of a uniform distribution results in a rectangular shape. It's just flat on either side, something like this. Here's A, here's B, and the probability of my random variable being something between A and B is this is my density curve, right there. This is not probability on this side. This is something else. This is the density value. The probability is the area. All right, more on that later. During certain time periods, okay, so this is an example, but it is a white slide, so I want you to pay attention and not skip this one. During certain time periods at JFK Airport, a New York City passengers arriving at the security checkpoint have waiting times that are uniformly distributed between 0 minutes and 5 minutes. as illustrated in the figure on the next page here. See it down here. Okay, so let's take a look at these probabilities. So, or at these properties. All of the different possible waiting times are equally likely. That's what we say when we mean uniformly distributed. That's a uniform distribution. Equally likely. And so it is just as likely that somebody will wait no time at all, 0 seconds, as it is that somebody will have to wait 4 seconds or 2 seconds. It's just equally likely. It all sort of just comes out in the wash as being the same. Okay, waiting times can be any value between 0 and 5 minutes. So it is possible to have a waiting time of 1.23456 minutes. By assigning the probability, okay, now that is not the probability, and that is not P of X. The area is the probability. This right here is what I'm going to call a density value. Okay, so by assigning the density value of 0.02 to the height on the vertical line in the figure, the enclosed area is exactly 1. Is that true? Let's see, base times height. Base is 5, height is 0.2. And 0.2 times 5 is indeed 1. Okay, so the area is 1. That's great. That's how, and that's one of the requirements, right, that's one of the requirements of a probability density function. Okay, in general, we make the height of the vertical line in a uniform distribution equal to whatever the range is. We divide 1 by that, so that when we multiply by the range again in order to get the area, we just get 1. Notice 0.2 is the same thing as 1/5. Okay, now this is an example here. So if you feel good about it, go ahead and skip this and move on to the next chapter. All right, waiting times for airport security. Given the uniform distribution illustrated in the figure right here, find the probability that a randomly selected passenger has a waiting time of at least 2 minutes. Okay, at least 2 minutes. So what would that be? At least 2 minutes. Well, I guess that would include 0, all of this stuff, all the way to, no, at least 2, forgive me. At least 2 means more than. So here's 2, and I want to include all of this here. So all of these possibilities are going to go into that probability. And so the probability is going to be this area. Remember, probability is area. And so what is this area probability here? Well, it has a height of 0.2. It has a width of, well, it looks like 3. And so that's going to be 0.6. Okay. And here's the solution. Yeah. All right, and that's that. Okay. There is another type of continuous distribution called the normal distribution. And this is very, very common. If a continuous random variable has a distribution with a graph that is symmetric and bell-shaped, we say it has a normal distribution. The curve is bell-shaped and symmetric, and this curve here is a very interesting curve. It has an explicit formula, y equals e to the 1/2 times x minus the mean of your distribution. So if you take the mean of your, you compute this average, and then you divide by a standard deviation of this one, square that, divide the whole thing by the standard deviation times 2 pi, very interesting formula. As it turns out, if I were to find the area, if I were to plot this thing and compute the area under this curve, now notice, this curve never gets to 0. Every possible value has some positive density value. And so any value is, in some sense, possible, all the way up to 1 million, 10 million, 30 billion. It's all possible, but those numbers become increasingly unlikely. And as it turns out, if you take the area under this infinitely long curve, it comes out to just 1. All right, which is good because that means it's a probability distribution like we hoped. Okay, standard normal distribution. The standard normal distribution is a normal distribution with the parameters. See, so the normal distribution has 2 parameters, mu and sigma. And for a normal distribution, the parameters are mu equals 1, and, nope, sorry, mu is 0. It's got the average is just 0, and the standard deviation is 1. The total area under its density curve is going to be equal to 1. Okay, finding probability when given z-scores. Right, so here's our distribution, and if we want the probability, we need to compute areas. Now, these, so it's measured, the x-axis here is z-scores because it's standard normal. And so 1, when x equals 1 in this case, because it's a standard normal, that's equivalent to the z-score being 1 because it is 1 standard deviation away, right? One standard deviation away. And so x equals 1 has a z-score of 1. So we talk about this in terms of z-scores. Remember, the z-score is the distance from the is x minus the mean divided by standard deviation. Okay. We can find areas, probabilities for different regions under a normal model using technology or a table, either technology or a table. There's no formula for this one. Technology is strongly recommended. Oh, certainly, yeah. Okay, but I provide a lookup table anyway, which I will discuss in greater detail later. Okay, finding probability when given a z-score. First, if using the lookup table, it's essential to understand these points. Okay, first, the lookup table. Is designed only for the standard normal distribution. Only for the standard normal distribution, which is a normal distribution with mean 0 and a standard deviation of 1. Each value in the body of the lookup table okay, so I'll show you what I mean by that, is a cumulative area from the left up to the vertical boundary above a specific z-score. When working with a graph, avoid confusion between z-scores and areas. The area of the z-score is the distance from the on the horizontal scale from the standard normal distribution, corresponding to the number of standard deviations above or below the mean. Refer to the leftmost column of the top row of the lookup table. Okay, we'll talk about that. The area is the region under the curve. So this thing here is on the x-axis. This thing here is the area. Okay, and then for Part of the z-scores denoting hundreds is found across the top of the row of the lookup table. All right, now, if you already know how to use the lookup table, go ahead and skip this example, but otherwise, we'll show you exactly what we mean about how to use this lookup table. All right, a bone mineral density can be helpful in identifying the presence or likelihood of osteoporosis. The result of a bone density test is commonly measured as a z-score. The population of z-scores is normally distributed with a mean of 0 and a standard deviation of 1. So these test results meet the requirement of a standard normal distribution. All right, and now the question is, a randomly selected adult undergoes a bone density test. Find the probability that the person has a bone density score less than 1.27. Okay, so find the probability that their bone density score, okay, so the scores are here on the x-axis, scores. And what's the probability that their score is less than 1.27? Well, 1.27, I guess, is right about here, right? And so probability is area. And so I am looking for the area over those scores that are possible. So we're talking about, or that we are interested in, scores that we are interested in. And the scores that we are interested in are less than 1.27. And so that includes all of these scores all the way up to here. So I need to find the area underneath this curve. Now, let's do this. We're going to do this two ways. First, we're going to use the lookup table. Now, the lookup table gives exactly what we are looking for in the sense that it tells us the area under the curve from negative infinity to z. This one, the z-score, the bound, the 1.2, it gives us all that area. That's what the table gives us. It gives us the area from negative infinity up to here. All right, let's take a look. So I'm going to go back to Canvas. I'm going to go to my home page where I've got all these links here, and I'm going to ICDC lookup table on February 21st, 22nd. I'm going to click on that, and there's the lookup table. All right, now my z. So notice I can find, I'm looking for the z here. And the z that I am interested in is 1.2. So I wish I could annotate this. I guess I wonder what would happen if I opened it in Notability. I wonder how Notability would feel about an Excel file. Okay, that's good, Okay, so here's my lookup table, and these are my z values. There's the first two digits of my z value, and here's the third. Okay, so I'm looking for z, I am looking for, z equals 1.27. And so I'm going to go here, 1.2, see that? And then 7, there's the 7 part. And I'm going to find, let's see, what is this? Right there. 1.27. And so I found that value. And I memorized that value, 0.8980. Okay, I come back. Oh, it was to here. And so the table tells me that the probability of z, big Z, being less than or equal to 1.27, my little z, is probability equals area, 0.8680. At least I think that's what it was. Let me just go back and verify that. No, it was 89. Okay, very good. And so that's my probability. So I use the table. Okay, but I could do that another way. I could use Excel. Okay, so I want to do that now. I'm going to open up Excel. I've got just some Scratch spreadsheet here. And so since it's Excel, I'm just going to kind of guess at what formula I need. Now it's normal, so I'm just going to try that one. So what I want here is P, the probability of Z, that Z is less than 1.27. All right, and so that is going to equal, enter, okay. I'm going to put that here now. Come on. Oh, it won't let me select, but the keyboard works. Well, I guess that's good enough. Okay, equals normal. Norm dist. Okay, let's see. X, mean, standard deviation, cumulative. This looks like the right thing. Okay, so X, well, X is going to be my Z-score, 1.27. The mean, because it's a standard normal, is going to be 0, and the standard deviation is going to be 1. Okay, now, do I want cumulative? Yes, I certainly do, because it's everything from negative infinity to 1.27. So I'm going to go 1 on that one, 1 for true. Press enter, and there it is. Exactly what I saw before, except this is more accurate. It's a probability, so I'm just going to round it to 3, to 3 decimal places, which would give me, so Excel, I use norm dot dist 1.27, 0 for the mean, 1 for the standard deviation, 1, I want it to be cumulative. That equals 0.89. It was 796. But if I round that, I do in fact get 80. So we'll just do that. Really, I'd like to just round it to 3 decimal places. So why? Okay, 3 decimal places. 3 significant figures, I should say. Okay, and that's how we did it. We talked about using the lookup table, and we talked about using Excel. And here's the interpretation. The probability that a randomly selected person has a bone density test result below 1.27 is 0.8980, shown as the shaded region, which I shaded. Another way to interpret this result is to conclude that 80, so this is a probability, right? And probability can be characterized as the relative frequency. So if I had 1 million people with 1 million bone density scans, the probability of finding somebody whose bone density was less than 1.27 is 89.80%. And so it's not wrong to conclude that 89.8% of people have a bone density level below 1.27. All right, now here is, okay, so that was an example. Here's another example. Bone density test. Finding the area to the right of a value. All right, so finding the area to the right of a value. Using the same bone density test, find the probability that a randomly selected person has a result above -1. Okay, so here's -1. Here are all the results above -1, and now I want to find this area. The table will not tell me this area explicitly because the table only gives areas to the left. This one is to the right. However, the sum, the total area, is what? Is 1. The total area is 1. and the book will tell me the brown area. So what I'm going to do is I'm going to, I'm sorry, I say the book, but I mean the table. So what I'm going to do is I'm going to, so 1, table, look up, brown area, and subtract from 1. Okay, let's do that. The table was found in Notability, so I'll go there. Now it was -1. It was -1. These are not negative values. Let me go to the next page. Here we go. These are negative values, and there's -1. -1.00, I guess is what I'm looking for. And that's this one right here. 0.1587. It's less than a half because I am on the I'm to the left of the mean. I'm way over here, so this is less than a half. I believe that. Okay. So this is 0.15. Oh goodness, I forgot. 87. And so I'm going to do 1 minus, so the red area, okay, so red area is 1 minus 0.1587, which equals 2, no, sorry, not 2, 8.8413. Let me just add that. Yeah, I think so. 8413. And so that is this total area right here, and that's what the probability is. So the probability of finding someone with bone density, we'll call it BD, greater than -1 is 84.13%. Okay, now if I were to do that in Excel, now does Excel make it easy for me? Well, let's just check. So if I wanted now the probability, P of Z, my score, the probability that that score will be P of Z greater than -1. Let's see what we get. Equals norm. All right, and I'm looking for like left tail, right tail. I don't see any of that. And so Excel really just gives you, it only gives you to the left. Now we want to the right. So what I'm going to do is, oh golly, all right. So what I'm going to do is I'm going to take, okay, there. I'm going to take 1 and minus what I get here. Look, see, look up at the top of my formula bar. So and then I'm going to do the normal distribution. So this is going to be -1 with a mean, and of course the mean is still 0, and the standard deviation is still 1. And for the cumulative, I want, okay, so -1, 0, 1, 1. I want it to be cumulative. Enter. 84134. 8413, and so that's what I find in Excel as well. So 2, Excel. 1 minus norm dist -1 0 1 1 equals 0.8413 also. Okay, great. So that's how I found the probability. Okay, and here's another example. Bone density test, finding the area to the right of a value. Okay, well now that's quite what I did. So I think this one, well, we'll see. Oh, the interpretation of it. Yes, of course. Because the correspondence between probability and area, we conclude that the probability of the randomly selecting somebody with a bone density reading of -1 or above is 0.8413. And so we conclude that 84.313% of people have bone density levels above -1. Okay, and now for the last example in this set, we're going to do between two values. Now, a bone density reading, now we want to know. So a bone density reading between -1 and -2.5 indicates that the subject has osteopenia, which is some bone loss, just some bone loss. Find the probability that a randomly selected subject has the reading between -1 and -2.5. So where is that? So that's here, -2.5 and -1. And so it does not include over here, no. And it does not include these values here, no, no. It just includes this area here. And how am I going to find that area? Well, I've got to be a little bit creative, because the only thing that the table is going to give me is area from -infinity all the way to some value. That's all the table is going to give me. So what I'm going to do, you might have already figured this out. I'm going to take the area from -infinity to -2.5, because that's the bit that I don't need. This bit here is good. I want that. But I don't need this. So I'm going to subtract that bit out and end up getting this right here. And so what's that going to look like? Well, let's see. So I'm going to go to the table. I want to find, so here's the idea. The probability that z is greater than -2.5 and less than -1 is equal to the probability that z is less than -1, take away, because that includes a whole lot, all of that. Take away the probability that z is smaller than -2.5, which is this represents the little area. The little area. Okay. And that difference gives me this. So I'm going to go to my table. I'm going to find the bigger area. Okay. Oh, whoops, nope, that's Excel. Go to my table in Notability. There we go. And so the bigger area is from -1, and the smaller area is from -2.5. This one here. That is a small area, 0.0062. And so I'm going to subtract those. And I should get 0.1525. If I subtract those, equals this minus, equals that minus 0.0062. Okay, let's write it down. Nope, not there. Okay, go back to Notability, this thing here. And this equals, okay, so this one here was 0.1587, and then I'm going to subtract 0.0062, and I end up getting 0.1525. And so that's this area. And I could have done the exact same thing in Excel. The probability that negative 2.5 is smaller than z, and z in turn is smaller than negative 1, that probability is going to equal, now I'm going to get norm dis, negative 1, 0, 1, 1, go on, cumulative, and then, well, the arrow, Excel, goodness, all right, enter. Oh man, how do I even get in that? For some reason, my touchpad is not, my touchscreen is not allowing me to get in there. I wonder why that is. Okay, anyway, I can move things around with this. All right, so, oh gosh, that is so annoying. Equals then, fine. Type it in again, norm.dist, negative 1, comma, 0, 1, 1, parenthesis, minus norm.dist, negative 2.501, 1. Okay, enter. All right, and there it is, 0.1525. So either way, we get that value there. And so what that tells us is that 15.25% of people have osteopenia. Okay. And there's the interpretation. 15% have osteopenia. All right, great. Okay, now, so let's, so if we wanted a generalized rule for finding the area between the two z-scores, we do that by finding the difference between the two areas found in the lookup table or found on Excel. My advice is to not memorize a formula in this case. Just draw the picture and think creatively about how to approach this area, how to get that area. Okay. All right, and so there's some notation here that I've already been using in Excel and other places. This is denotes the probability that the z-score we're interested in is going to be between A and B. So remember before with something like Poisson where you had x, and it was the probability that x equals some little x value, the probability that x equals 1. That's the same thing here, except now we're talking about z being within intervals. Because the probability of z equaling any particular thing is 0 with continuous random variables. So you really only talk about intervals, and that's why we use the density curve, and that's why we use areas under the curve. Okay. This thing here then denotes the probability that the z-score is greater than A, and then this other one is for when the z-scores is less than A. All right, so if you need to find a z-score and you have know the area, so it gives you the area. See, so we're going backwards here. So this is backwards. All right. I am given the area from the left, and I need to find the z-score. And my advice is to draw a bell-shaped curve and identify the region under the curve that corresponds to the probability given. So if they tell me that you know that the percentage of people under this unknown score is 20%, what is the score? What score is that? And so they give me the area. Identify the region under the curve that corresponds to the given probability. If that region is not a cumulative area from the left, then you're going to need to work instead with a known region that is a cumulative region from the left. Use technology or a lookup table to find the z-score. Then use technology or a lookup table to find the z-score. Now, if you're using technology, you need to use the inverse distribution. So this is norm dot inverse. That gives you the inverse function, the opposite, the function that gives you the z-score out. All right, look up with the lookup table. Use the cumulative area from the left. Locate the closest possible probability in the body of the table and identify the corresponding z-score. Okay. Now a critical value. For the standard normal distribution, a critical value is a z-score on the borderline separating those z-scores that are significantly low or significantly high. There it is again, significantly low, significantly high. Remember, we want to determine whether our sample is significantly low or significantly high. If the sample is significant, we will be rejecting the null, rejecting the assumption. All right. Critical value. Okay, so here's a notation. So the critical value is that value on that separates significance from not significance. And here's the notation. The expression z with a subscript of alpha looks like an A, but it's a Greek letter, denotes the z-score with an area of alpha to its right. Like this. So there's z alpha has an area of alpha to its right. Okay, now let's take an example. Finding the critical value, z alpha. Find the value of z sub 0.025. And so what? Alpha is 0.025. So we need to find this, we need to find where this area here, where the area is 0.025. All right. Now, if we want to use, and so that's what we're going to do now in this example. Now, notice that this thing here is symmetric. All right, so this thing is symmetric. And so what that means is that whatever you see on one side is exactly the same on the other. So the area, if there is an area of 0.025 on this side, it will take you to some z value, right? Some positive z value. That same z value on the negative will also give you the same area. Same area over here. So I'm going to cheat a little bit. I'm going to find the area here that is 0.025, which is a cumulative area from the left, which is what the table is going to give me. And I'm going to find what value it is. And then I'm going to change its sign and bring it over here. Okay, so let me show you how that's done. So first we're going to use the table. Alrighty. So for the table, I go to other notability. Right there. All right, now I'm looking for, it's going to be negative, certainly, and the area is going to be 0.0025. So I'm looking for that area. The area. Remember, the body gives me the areas. 0, 1, 3, 1, 3, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5. There it is, 0, 2, 5. What is that? That is negative 2.8, right? Negative 2.8.1. So negative 281. Negative 281 gives me that area. Now let me just make sure that was the right area. Go back. Here. No, it's the wrong area. It's just 1 0. Dang it. Okay. Not 281. 2, okay, we're getting close. Oh, there it is. Negative 1.9. Negative 1.96. Negative 1.96. So that's the area. And so this area here of 0.025 corresponds to a z value of negative 1.96. So that means that that's going to be the same over here, 1.96. And so I conclude that z 0.025 equals 1.96. Now, what about Excel? All right, let's go. So we're going to do the same thing because remember, Excel only also gives me area to the left. So I need to find what area to the left I'm interested in, and that happens to be the same value. Now let's go ahead and take a look at Excel. So I go to Excel. I get my keyboard out. All right, now this one here I'm looking for z sub 0.025. Now, in order to get that, I'm going to go equals norm dot inverse. The inverse distribution. And it says probability, which is area. So that's going to be 0.025. Now I need to put in the mean, which is 0, and the standard deviation, which is 1. And I'll press enter. And there it is, negative 1.96, basically. Notice how much more accurate it is, though. And so that's how I do it. Let's just take a look. Can we look at the formula again? I don't think I'll be able to modify it, but we can look at it. Norm.inverse. I don't know why. I shouldn't take time to do that because you can always go back and look at it. All right, and so there it is. So that is, so the z alpha, did I already write that? Z alpha equals 1.96. Yeah, I wrote that right up here. Okay. So Excel does that as a 2. All right, now this is basically section 6.2 now. And we just have a few more slides. This section presents methods for working with normal distribution that are not standard. So normal distributions that are not standard. That is, the mean is not 0, and the standard deviation is not 1 or both. The key is that we can use a simple conversion that allows us to standardize the data, any normal distribution, so that the same methods of the previous section can be used. So that's the beauty of it. The Excel and the table, well, actually, Excel, you can put in whatever mean and whatever standard deviation you want. But of course, the table requires a z-score to look up and find the area. You need a z-score. And remember, to find the z-score, z equals x minus mu over sigma. And that's what you're going to do. So you might have a normal distribution that does not have mean 0 or standard deviation 1. You can still use that by standardizing it. And I think that's what this is. Look at that. That's just exactly what I had before. All right, round to 2 decimal places because that's what the table takes. The formula allows us to standardize any normal distribution so that x values can be transformed to z-scores. Look at this conversion. So here you have the mean is mu, and x is just sort of right there. And you have this standard deviation, something like that. And then the z tells you how many standard deviations. So that's how you go from, that right there is the golden ticket. That takes you from a normal distribution, a non-standard normal distribution, to a standard normal distribution. The figure illustrates the conversion. All right, that's fine. Okay. Procedure for finding areas with a non-standard normal distribution. Well, here's what you do. First, you sketch. Sketch a normal curve. Done. Label the mean, 68, and any specified values, and then shade the region. 68, they said 59. No, I'm just making these up. 72, and I shade the values. Now, if I wanted to find that area, I'm going to need to standardize and go to the table, and that will give me the area for that curve. Okay. For each relevant x value on the boundary, use the formula there to convert that value to the equivalent z-score. With many technologies, this step can be skipped. Yes, that's true, because Excel has norm.dist, where you put in the x, and you put in the mu, and you put in the sigma. And then you're probably just going to want 1 for cumulative. You do not have to standardize. Okay, use technology software. Use technology software or a calculator or a table or a lookup table to find the area of the shaded region. This area is the desired probability. Area equals probability, folks. Area equals probability. Okay, here's an example. What proportion of men are taller than 72 inches? So, height requirement for shower heads. All right. Heights for men are normally distributed with a mean of 68.6 inches and a standard deviation of 2.8 inches. Find the percentage of men. See, so height is standard, is a normal random variable. And so we can use that fact to get a probability of men who are taller than a shower head at 72 inches. And studies have just shown that this is an accurate way to do it. If you were to sample like 100 or 300 men, what percentage of them is higher than 72 inches? It's what we're going to find. This thing really works. Okay, so the mean is 68.6. The standard deviation is 2.8. This is inches, this is inches. So the z-score is going to be 72, that's my x, minus the mean, which is 68.6 over 28. And that's going to equal, let's see, I'll just put in my calculator. 72 minus 68.6 equals that, 3.4, divided by 28. 2.8, sorry. And that gives me 1.214. Okay, now I'm going to do what I should have done first is draw my normal distribution. There it is. And there's my 68.6, and the standard deviation is 28. And then there's this 72. Well, that's going to be like, whoops. That's going to be like over here. And they want to know what's the probability of someone being taller than. Well, that's going to be, 73, 74 inches over here. And so that's what I want. Well, it goes to the right. Okay. So I find the z-score, and the z-score, it turns out, is 1.217. Now, it's symmetric. So if I come over here to negative to 1.214, negative, that's going to give me some area to the left. And that area is going to be the same because of symmetry. So I'm going to go to my lookup table, and I'm going to try and look up negative 1.214. Now, actually, I'm going to need to round this. I'm going to go ahead and round this to 2 decimal places. And so that would just be negative 1.21. So what? So here I go to my lookup table. Okay, negative 1.21 is right there. So it looks like 11.31%. This thing? There. So the table told me 0.1121. And so so I conclude that 11.21% of adult males have a height of greater than or equal to 72 inches. All right, so they're going to have to bend down a little bit in the shower. So there you go. Okay. Great. So there's that one. Oh, and here's the interpretation. This, as you can see, we found the exact same thing. About 11% may find the design to be unsuitable. Okay. Finding values now from known areas. Here are helpful hints for those cases in which the area or the probability or percentage is known, and we must find the relevant values. So graphs are extremely helpful in visualizing, understanding, and working with normal probability distributions. So they should always be used. Always just draw a graph. Now don't confuse z-scores with an area. Z-scores are the distance from the horizontal axis, but areas are the areas are the areas of the regions under the curve in the lookup table. And they're given to you in the lookup table. Okay, next thing. Choose the correct right-left side of the graph, like we did, because it was taller. We were looking for people who were taller than 72 inches. We wanted to the right. A value separating the top 10%, for instance, is going to be located on the right side. All right. And then the z-score must be negative whenever it is located in the left half of the normal distribution. And then lastly, the areas. The areas or probabilities are always between 0 and 1 and are never negative. Okay. So, the procedure for finding values from known areas or probabilities is to sketch a normal distribution curve, enter the given probability or percentage in the appropriate, and identify the x value that's being sought. Then, using technology, find the right Excel function if using a lookup table, refer to the body of the table and find the area that's closest to find the lookup body of the lookup table to find the area to the left of x. Then identify the z-score corresponding to that area. Once you know the z-score, you must convert it back to its equivalent x value. And so in order to do that, you take sigma times z and add that mean. Next, refer to the sketch of the curve to verify that the solution makes sense in the context of the graph and the text and in the context of the problem. All right, let's take a look at this example. Goodness, look at all these words. When designing equipment, one common criterion is to use a design that accommodates 95% of the population. We have seen that only 46% of women satisfy the height requirement for U.S. Air Force pilots. It's interesting there's a height requirement. Only 46% of women. Goodness. Okay. What would be the maximum acceptable height of a woman if the requirements were changed to allow the shortest 95% of women to be pilots? The shortest 95% to be pilots. That is, find the 95th percentile of heights of women. So what would that height need to be? What would the height requirement need to be in order to allow 95% of the shortest? Okay. Assume that heights of women are normally distributed with a mean of 63.7 inches and a standard deviation of 22.9 inches. So look at that, a little bit more than the men's standard deviation, which is 2.8. In addition to the maximum allowable height, should there also be a minimum required height, and why? All right, what have we got here? Let's go ahead and do this one. So, I didn't give myself much room here. All right, well, we just want the 95th percentile, right? So, I'm going to draw my, we could do better than that. I'm going to draw, okay, there's that. I'm going to do, so I want the 95 shortest, the 95% shortest, so there's 95. So that's going to be 0.95. And I just need to find that z-score. What is the z-score that gives me 0.95? And so I'm going to go, well, should I use the table? Let me go ahead and use the table. Go back here. Table. This is definitely going to be a positive thing, right? Because it covers so much area. This is for a different table. All right. So 0.9, there's 9.6, 9.5, 955, somewhere in between here. Somewhere right in between there. So maybe what I'll do is I'll go 1.645, split the difference. 1.645, all right? That's the z-score. That z-score means that there's 95% lower than it. Sorry. So z here equals 1.645. But I don't want the z-score. I want it non-standardized. So I'm going to multiply that z-score by the standard deviation. So that's going to be 2.9 times 1.645 plus mu, which is what? 63.7. Right, let me see what I get here. 2.9 times 1.645 plus 63.7. Enter. I get 68. So it needs to be 68.47 inches. So pretty close to 68.5 inches. That's what the requirement needs to be. Okay, now let me use technology, and maybe we can demonstrate that we don't need to standardize here. So what I'm looking for is P95, the 95th percentile among heights, women. And I'm going to use the standard deviation to give me that. And I'm going to go equals norm. Okay, now I am not looking for the probability. I am looking for the z-score, or in this case, the x-score of the x, the data. I'm going to use the inverse, and it gives me the probability. Well, the probability is 0.95, because it's 95% of the population I want to be contained in this area, comma, the mean was, what was the mean? 63.7, comma, what's the standard deviation? That was 2.9. So I filled those things in, and now I press enter. 68.47. That's exactly what we had before. I put in the mean and the standard deviation into the normal dot inverse function. And it gave me just what I had seen from before. All right, so a requirement of a height less than 68.5 inches would allow 95% of women to be eligible as U.S. Air Force pilots. And there should be a minimum height requirement so that the pilot can easily reach all the controls. Yeah, yeah, very reasonable, it seems. Alrighty. Okay, that's it, everybody. Good luck on the homework and the lecture quiz. And the content quiz on contingency tables if you haven't already taken it.